Hi Chem 100, this is Dr. Ricardo. We're going to start chapter 12, which is on solutions. I don't have formal notes for this chapter, so what I did was I went through what I thought was very important from the core chemistry skills that are in the back of the chapter. So for chapter 12, it starts on page 391. So I'm going to use that as my reference for the video. All right, so the first thing we want to talk about in terms of solutions is just the general concept and three terms. When we mix things together, we can ask ourselves, how are those things mixed? If those things are mixed all the way down to the individual molecules or individual ions, then the solution is, the material or the mixture is said to be a solution. So one of the things you remember from the very beginning of the year was a solution was a homogeneous mixture. Right? So we put the different substances together in the mixture. Let me make this just a little bit bigger for now. Okay. We put the substances together and they're going to be mixed all the way down to the individual molecules. So we can make solutions that are made up of gases for the solutes, for the individual things, and the background matrix can also be a gas. We can make solutions where you have a gas and the gas is dissolved in a liquid. Right? So there's oxygen that's dissolved in water all the time, otherwise the fish wouldn't be able to breathe, right? Fish breathe oxygen just like we do, only they extract the O2 that's dissolved in the water with their gills, just like our lungs extracts the O2 that's in the air. So you can have a gas in a liquid. Carbonated water is another example of this. So seltzer water is a gas that's dissolved in a liquid. Okay, so the carbon dioxide, not when it's fizzing, but right before it fizzes, right before you open the cap, the carbon dioxide is dissolved into the water all the way down to the individual molecules. Best example of a solution of a gas inside of gas is air. Right? So air, we have a mixture of gases. The one that's in the highest percentage is N2 gas, right? It's at 80%. And oxygen is around 20%. Now, there obviously are other things that are in air, but these are the two big constituents. So the one that's in the smaller quantity, and gases always dissolve in other gases. There's no situation where you can take gases and they hate each other and they stay on the separate side of the rooms. If you put things in the gas phase together, they will always mix all the way down to the individual molecules. So gases inside of gases are always solutions. Okay, you have to be careful with other things. Do you have big bubbles? Do you have clumpiness? It might not be homogeneous. Okay, so solutions are defined as homogeneous. All right, so in this particular case, which one is the solute and which one is the solvent? Well, first of all, the whole thing, the mixture, is called the solution. Okay, so when you put all the parts together, you get a solution. The one that's in the higher quantity, we call the solvent. So we're asking, since oxygen is in the lower quantity, what do we call the one in the lower quantity? We call it the solute. So sometimes we can ask, how much solute can we put in the solvent, and what would be the concentration of the solution? Okay, so a couple of more examples. You can take a liquid, right, like lemon juice, and dissolve it up in water. So that would be a liquid in a liquid. Well, the ones that we're most familiar with, you can take a solid and dissolve it up in a liquid, right, like an ionic solution, like a salt. So an example of that would be salt water. So if I had NaCl aqueous, right, that would mean that I had a solution. And here's my beaker. Got a solvent of water. I put in the individual salt, right? Here's some sodium chloride salt. This is a solid. Okay, I put it in, and I wait for it to dissolve. I wait for the individual molecules to spread out. Now, you know NaCl is made up of individual sodiums. We'll call those X, and we'll call these guys O. So when these dissolve, they spread out into the individual ions are dissolved in solution. And if I drank some of the water from this top corner, it would taste just as salty as if I drank it from here, because it's truly mixed in as a solution, mixed all the way down, in this case, to the individual ions. There's no clumpiness. A solution doesn't have anything left on the bottom. If it has anything left on the bottom, you don't count that part as the solution. The solution is the homogeneous liquid on the top. All right, so next thing that we're going to quickly review is the idea of the solubility rules. So for that last group of solids dissolved in liquids, let's take a look at some of the rules that we learned for what dissolves in what. Okay, so we're hyper-focused on aqueous solutions, solutions where water is the solvent. Okay, so water, we're dissolving things up in water. Okay, so these rules that are listed here in the back of the chapter, we've been talking about on this reference sheet that you should still have and you can use to take the test. Okay, so up at the top, it talks about all of the different substances that are normally soluble, and it lists the ions by the anion. So if this anion is soluble, it means that every cation, like this particular case where there's no exceptions, no matter what the cation is, no matter what the positively charged metal part of it is, it's going to dissolve. So nitrate is universally soluble with any kind of metal. Same thing with acetate. The other ones are generally soluble if they're on this top list, but there's some exceptions. So the three halogens pretty much have the same exceptions: chloride, bromide, and iodide. They are soluble with all compounds except silver, mercury 2, and lead 2. And then the last one who has exceptions, sulfate is generally soluble, except when you find sulfate with strontium plus 2, barium plus 2, or again, mercury 1. So mercury 1 is not very soluble. Okay? And then down at the bottom, we have the anions that are generally insoluble, that form participates with everything except with these exceptions. So these things would form at the bottom. They would not dissolve unless it's with the universal solvent ammonium. Ammonium is soluble with everything. Look, it's on every single one of these lists. So the thing that dissolves with any anion is ammonium ion. The anion that dissolves with any cation is the nitrate ion. So if you take ammonium nitrate, that's always your best bet, because this is soluble with everything and this is soluble with everything. So ammonium nitrate is really, you never have to worry about this thing forming a precipitate, right? This is incredibly soluble, and so is this. So this will be aqueous under any circumstance. It's made up of the universally soluble cation and the universally soluble anion. Okay, but sometimes you need to get other ions into solution, so you're going to try to get them in, if you want them to dissolve, in a form that's soluble. So you're going to pick one of those forms up at the top. These ones down here, sulfide is generally insoluble, except in these situations. Carbonate is generally insoluble, except when it's with a group 1 anion or ammonium. Phosphate is generally insoluble, except when it's with ammonium or group 1. And then hydroxide is generally insoluble unless it's with ammonium, calcium, strontium, or barium. Okay, and we know group 1. Group 1 is lithium, sodium, potassium, rubidium, all those guys from the very first all the way on the left side of the periodic table. Okay, these are generally soluble. They're small and tight, and water solvates them very well. Okay, let's take a look at this example. I'll blow it up again. Okay, because it illustrates one really important point. and that is this idea of the net ionic equation. So that's what I want to review with you just a little bit now. Okay, nothing new. So if I ask the question that they're going to ask over here, determine if an ionic compound forms when a solution of calcium chloride and potassium carbonate are mixed. Well, obviously, if these two things are already solutions, then we don't have to worry if they form soluble salts or insoluble salts. They must form soluble salts because I'm mixing the solutions, right? So I have these two things already. So I'm going to write out the equation, but I'm also going to draw the beakers for it. Okay, so here's my calcium chloride. We know calcium's in the +2 state and chloride's in the -1 state. I got that by reverse crisscrossing. It's aqueous. And the question that they're asking is, does it react with potassium? Potassium's always in the +2 state. Carbonate, -2 state, aqueous. Okay. So what happens when you put these two things together? Okay. So we're asking the question, do these two things react? Now, when you look at it, the reaction that's going to occur is going to depend on if potassium is insoluble with chloride and calcium is insoluble with carbonate. If the other guys that get together after the switch are all soluble, it's kind of like nothing happened, okay? Because everything would be dissolved. So I'd mix the two solutions. This would have ions mixed in it. This would have ions mixed in it. Put them together, it would just be more ions mixed in. In order for me to see something happen, I've got to form a precipitate. Okay? So let's take a look at our solubility rules now. And first, this is double replacement, right? Calcium, let's ask what happens when calcium gets together with carbonate. So if you look over here, where's carbonate? Carbonate is down here in the insoluble section, right? Here's carbonate, compounds that don't dissolve. Okay, well, what are the exceptions? The exceptions are ammonia and the group 1 metals. Well, calcium is not a group 1 metal, it's from group 2. So that means when calcium and carbonate find themselves in the same beaker, they're going to hook up like you wouldn't believe, okay? They're going to get together, make this a little smaller. They're going to get together to make what product? Ca+2 crisscrossed with CO3 -2. Well, that's perfect, right? +2 goes together with -2, and we just found from the chart that that guy is soluble. Okay, well, what about the other guy? Maybe that one is insoluble too. Well, the other one has to be potassium and chloride. Okay, so go up here for chloride. This on the top are compounds that are generally soluble. Here's chloride. So chloride would be soluble except if it was with silver, mercury 1, or lead. Okay? I don't see silver, mercury 1, or lead. I see potassium. So that means these guys do stay in solution. So they're aqueous. Okay? And in double replacement, if you remember, no one's oxidation state changes. Everybody just stays the same. So the last thing I have to do is I just have to balance this. So to balance it, I'm going to need a 2 over here to fix the 2 potassiums. That takes care of chloride as well. All right, I might do it. I got 1 calcium, 1 calcium, 1 carbonate, 1 carbonate. Okay, let me show you what's really happening. Here's my beaker on the left. It's got calcium ions floating around and chloride ions floating around. And there are 2 of these for every 1 of those when it breaks down. When this breaks down, it breaks down into its individual ions. So this top reaction is called the overall reaction. Underneath, I'm going to start what's called writing the ionic reaction, where I show everything as the ions that they really exist. So that's an ion plus 2 Cl2 minus. That's what's really happening in calcium chloride aqueous. It's really broken down as individual ions floating around in the water. The solution is water. Okay. How about this beaker? This beaker, I have 2K pluses floating around for every CO3 minus 2. So I've got millions and millions of them, but I'm just going to depict one set. Okay. But that's the key. They're floating around. They're free to move. The whole thing is neutrally charged because the positives balance off the negatives, just like here. So this one is also aqueous, means it's also dissolved. So I break them up and show them as their individual lines. Don't write K2 because they're broken up into individual potassiums and carbonate. So that's what's really happening. Okay, if I take this one and dump it into this one, I should have left myself more room and made a beaker smaller, and I throw them into one beaker. Wow, what's going to happen is, boom, this thing is going to become completely cloudy white. It's going to become completely cloudy white because the calcium and the carbonates, the calcium and the carbonates are going to find themselves, make a precipitate, and if I wait about 10 minutes, that stuff is going to settle down to the bottom, and I'm going to get a whole load of calcium carbonate solid at the bottom. So this one I don't break apart because it's a solid. I only break apart the ionic substances that are dissolved in solution. So these I show as ions. This one I leave alone because it really is a solid at the bottom. And the last one is an ion like I would find it in solution. So I write 2K plus and my 2Cl minus 1 aqueous. Okay, so this reaction here, a little smaller, this is called the ionic equation. The next thing we're going to write is the net ionic equation. Net means just show the important stuff. Just show stuff that doesn't cancel out. Something that's not going in but also coming out the other side. Get rid of anything that is just going around in a circle. So I'll give you a business analogy to that. If you have a hamburger restaurant and in the morning you have to go out and buy all the meat and the cheese and the soda and all the different things, and it costs you $150 to buy all the stuff, and then you sell the hamburgers, and at the end of the day you look in the cash register and there's $200, right? Well, guess what? 150 of it were the costs, the fixed costs to buy the hamburgers and the cheese and the buns and the soda. So your net is only $50. You take $200 minus 150 for everything that you put in, and you net 50. Well, that's the same thing that's going on here. You see these two potassiums? They're over here, but nothing happened to them. They just stayed floating around in the solution the whole time. Same thing with the chlorides. Those things were boring. They just floated around the whole time. It's the calciums that hook up with the carbonates and head for the bottom. These things are just floating around. Look, those 2Ks and those 2Cls, nothing happened to them. So if nothing happened to them, we cross them out. Look, 2 there and 2 there, 2 here and 2 here. So this is a new concept. It's called the idea of the net ionic equation. The real deal, what's really happening, is between calcium and carbonate. So calcium aqueous from this beaker gets together with carbonate aqueous from this beaker. When you mix the two beakers together, you pour one into the other. And the new thing, right, is calcium carbonate solid. Those other guys were just watching, okay? Some people call them spectator ions. They just watched, okay? So this is called the overall reaction. This is the ionic reaction, and this is the net ionic reaction. Get down to what really happened is going to cross out everything that stays the same on the left side and the right side. All the ions that were just in the beaker watching the reaction occur are called as spectator ions. Good? Okay. All right. Next thing we're going to talk about is when we make a solution, we're interested in how concentrated it is. Okay? So we can talk about it qualitatively or quantitatively. Qualitatively, a solution that has just a little tiny bit of solute in a lot of solvent. So maybe you take a few sprinkles of sugar, put it in water, mix it up, and the water can just barely taste sweet. You can hardly even notice. Well, that would be called a dilute solution, when you only have a little tiny bit of solute in the solvent, right? The solvent is the base. A concentrated solution would be to take 50 grams of water and mix it into 50 grams of water. So 50 grams of sugar and 50 grams of water, right? That's a 50% by mass solution. That would be incredibly concentrated, right? It would be thick like syrup. So concentrated means a lot of solute in the solvent, in the solution. Dilute means a little tiny bit of solute in the solution. Okay, but we want to go past just talking about it in a qualitative sense. We want to put numbers to this, right? How strong the solution is how concentrated it is. Well, there's going to be 4 different ways that we're going to talk about it. Okay, first 3 are very intuitive, and you kind of see this all the time in life, so they're not going to require a lot of explanation. Okay. So the first one is called mass percent, M over N. So you could do percent M over M. The M in the numerator is the mass of the solute, the thing that's dissolving. The M in the denominator is the mass of the whole solution. It's not a ratio of the solute to the solvent, okay? It's a percentage, which means the denominator includes everybody. It's the total mass. This is the total mass. In the numerator is the mass of the substance that you're interested in, the mass of substance A, okay? So the bottom is the total. So let's take a look at the formula. All you need to do is take the mass of the solute and divide it by the mass of the solution. Okay? So our first example that we just talked about is if I had 50 grams of sugar, okay, and I mixed it into 50 grams of water. So don't put 50 grams of water, that would be the mass of the solvent. The total mass of the solution is 100 grams of water and sugar. Masses are fundamental. They don't change. When I add 50 to 50, I get 100. There's nothing that can happen. Always mass is conserved. So 50 divided by 100 times 100, this would be a 50.0% solution by mass. Very, very sweet water. Okay? Some people call this simple sugar, and you'll see it in the restaurants. Okay? So that's the way you would do that one. Okay? All right. Next one. You can do percent by volume. Sometimes you'll see this with shampoo. Okay? So if you take an active ingredient of like linoleic acid, and it says it's 5% linoleic acid by volume, what would that mean if something was 5% acid by volume? It would mean you have 5.0 milliliters of the linoleic acid over in every 100 milliliters of the product that you're making. In this case, that would be shampoo. Over the total. This guy over here is the total, right? Not just the water that you put in. So 5 over 100 times 100, right? To make it percent, sorry, times 100 would give you 5%. Okay, so a lot of times you'll see that. Nothing special about that. Volume, the volume of the whole thing. This is a weird one. Okay, you'll see once in a while on consumer products. You take the mass of the stuff that you're interested in and you divide it by the volume of the solvent. Okay, oh, excuse me, of the solution. So for instance, this would be a 5% M over V mass percent of sugary water would be 5 grams, right, per liter of water, right? So you put the volume in the denominator. Actually, you do it in milliliters. So if you took 5 grams and you put it in a total of 100 milliliters of solution, you'd have 5 divided by 100 times 100 would be 5%. So the thing that you have to be careful of with is that when the sugar dissolves in the water, the volume could adjust a little bit. So the way you make a 5% M over V solution is you have to be a little bit careful. You can't just take one thing and throw it in the other like you could up here, right? Here, you just take 50 grams of water, 50 grams of sugar, throw them together, and since the denominator is mass, you don't have to worry about did it contract a little bit or did it expand a little bit. Over here, you kind of did have to worry a little bit. You have to take the linoleic acid, dissolve it up in about 90 milliliters to make 90 milliliters of the shampoo total, and then put the last 10 in just to make sure that the total comes out to 100. So let's do it over here. Let's make a 5% M over V salt solution. Okay, so if you want to make that, well, just be careful. We want the mass over the volume, right? So the volume we want to be in milliliters. So this is going to be milliliters of solution. But the solution isn't already made up. You're kind of making it on the go. And this is the mass of the salt. So we weigh out 5 grams of salt. We put it in our beaker. Right? This is the line that I have to fill up to make 100 milliliters. Right? Because I want to do a 5% solution. So I want the total volume of the solution to be 100 milliliters. So the first thing I can't do is I can't just take 100 milliliters of water and pour it on top, because the volume, this sugar is going to take up some space even after it dissolves, so the volume is going to be higher than 100. It might not make it all the way to 105, but it would definitely be like 103, 104, something like that, right? So to do this right, what you do is fill it up to about here with water, get it all to dissolve so that you get the solution almost totally made, and then at the end, top it off with a little more water so that you bring the total volume up to 100, okay? And you see the reason why? You have to just be a little bit careful, because this takes up some of the volume. You can't just take 100 milliliters of water and throw it on top. You'll have too much, okay? Again, the denominator is the volume of the whole thing, of the solution. That's the water and this, okay? So you want to bring the volume up to 100 milliliters. So if I do that, I would take my 5 grams, divide it by 100.0 milliliters of solution, times 100 to make a percent. That 100 comes right out of the formula. Give me 5%. Okay. And so those are all the 3 different ways we can express concentration. You can do mass percent, volume percent, or mass over volume, M over V. The next one is really the most important thing that we're going to teach you in this chapter, and that is a new term called capital M. It's the molarity of the solution. Okay, so there it is, the molarity of the solution. Okay, so the molarity of a solution is the moles of the solute, not the grams, or the volume, or the milliliters. It's the moles. So take the mass that you have, divide it by its molecular weight to get the moles. Per means in the denominator, per liter of solution. Not liter of solvent, liter of solution. So if I want to make a 1 molar solution of NaCl, now, I'm going to make the easiest version. I'm going to make a whole 1 liter of it, but you don't have to make a 1 liter. Maybe you don't need a whole liter. Maybe you need a lot less. So you can scale it down, and I'll show you how to scale it down. But right now, let's keep it simple. I get a 1 liter volumetric flask. This is a really cool looking device. It's a flask that looks like this. You've seen this. Okay? It's very accurate. It's got a line up here. If you fill it up to that line with solution, you'll have exactly 1 liter of solution. How would I go about doing this? I need to take 1 mole of my salt. And here's the pile of salt on the side. We secretly know that sodium chloride has a molecular mass of 58.5. This guy's 23, this guy's 35.5. So the molecular mass is 23 plus 35.5 for chlorine comes out to 58.5. So not only is it 1 mole, but if I had to weigh it out, that turns out to be 58.5 grams of salt. So I take my 1 mole, which happens to be 58.5 grams, and I put it in here first when this is still empty. Okay? Sometimes you get it's called a powder funnel. You put the funnel in, this way all the salt can go in. Right? So this is a pile of regular table salt, and it's sitting at the bottom. The next thing I do is don't just right away fill it up with water all the way to the top, because these two things have to interact. The sodium and chloride ions have to dissolve in the solution. So what you should do is fill it up about halfway, because now you can still swirl it. Fill it up halfway, get it to totally dissolve first. Then you fill it up a little bit more, get it to totally dissolve, and then swirl it, swirl it, swirl it. When that's filled it up, then you bring it up to the volume at the end. Can't just dump 1 liter of water on top, you'll have too much. You want 1 liter of solution and 1 mole. Now what happens to that sodium chloride ions? They're going to be equally distributed throughout the whole solution. They're dissolved. So this pile at the bottom would go away, and the ions would be floating around. The individual NaCl aqueous ions are really Na plus aqueuses and Cl minus aqueuses, surrounded by water molecules. This is the way ionic salt dissolves, as individual ions. And there they are, all dissolved. It would be salty water. The whole thing has no electrical charge because it has exactly the same number of sodium ions as chloride ions. Okay? All right, so new formula. Molarity is equal to the moles of solute over the liters, over the liters of solution. Moles of solute over liters of solution. Okay, well, let's rearrange this to another really important thing. If I have a solution, I have a certain volume of solution, okay? A certain volume of solution, and I know what its concentration is. I know how much of the active ingredient I have in moles, because moles, this is maybe just as important as the other way, moles, bring this liters up to the left, multiply both sides by liters. Moles is equal to the molarity, how concentrated the solution is, times how many liters you have. Hey, if I only have half a liter, and I pour half a liter in it, and I dissolve away, and I evaporate away all the salt, how much salt would be there? Half a mole, right? Because this would just be half a liter. Now, half a liter probably got to go down a little more because of the shape, okay? If I had 2 liters, I'd have 2 moles, so it scales appropriately. So anytime you want to know, this is a new way for stoichiometry to get the moles, right? Not only can you get the moles of something by taking its mass and divided by its molar mass, there's a new cowboy in town. We can get the moles by taking the concentration of a solution times how many liters you have, okay? Very important, 2 super important formulas. Molarity is moles per liter. This just says solution. Don't forget, the denominator includes everything. No percentage, just moles per liter is molarity. Okay, let's do a problem. This last one down at the bottom, I'll just read it to you. What is the mass percent, the mass volume percent, M over V, and the molarity of a 225 milliliter solution of lithium chloride that contains 17.1 grams of lithium chloride. Okay, so for the first one, if I want to do M over V percentage, I just leave this numerator alone. I take the grams of the solute. The solute is the lithium chloride, so 17.1 goes in my numerator. Okay. What goes in the denominator? The definition up here of mass percent is the grams of the solute divided by the milliliters of solution. So I leave that alone. 225 goes in the denominator, and then I just multiply by 100. Okay? It's a very weird unit because it has different things in the top and the bottom, but some people do it. So this mass per volume would be 7.6% because 17.1 divided by 225 gives you 7.6%. This is not super critical for us. This one here is. Okay, go back to the beginning, the question. What is the molarity of 225 milliliter solution that's made up, that contains 17.1 grams of lithium chloride? So first thing, if I want molarity, I need moles per liter. So how do I get the moles? I take my 17.1 grams, divide by the molar mass of lithium chloride. Lithium chloride is 42.39 grams per mole. Okay, this comes right from looking up lithium and chloride on the periodic table. That's its molar mass. So if I do that math, I get 0.403 moles of lithium chloride. What's our definition of molarity that we just learned? It's the moles of solute in the numerator. So just take that number, put it in the numerator, divided by the liters of solution. Well, they gave us the liters of solution, only they gave it to us in milliliters. Right? This 225 is not water. This is the amount of solution I have on hand, right? What is the what is the molarity of a 225 milliliter solution of lithium chloride? So just have to take this and change it to liters. 225 milliliters is 0.225 liters. Okay, that goes in the denominator here. And last step, moles divided by liters has the unit capital M. So molarity not only has the symbol capital M, but its unit is capital M. 0.4 divided by 0.225 gives you 1.79. This has 3 significant digits. This has 3 significant digits, so should your answer. So 1.79 molar lithium chloride. That's the concentration of the solution. Okay? Okay, 2 more cool topics, right, is using our new tool, right, that we know that a way to find out the moles of something is the concentration times the volume of a solution. So let's make this a little smaller. Let me show you how those work. So this section is called using concentration as a conversion factor, right? Or product for a reactant or product in a chemical reaction. When we need to calculate the amount of solute or solvent, we can use the concentration as a conversion factor. So instead of using a formula that say moles is equal to molarity times liters, getting the moles and then doing what we usually do with all the crossing out, we can build that right into the question by using concentration as a conversion factor. Because, in a sense, molarity is the number of moles of the solute per liter of solution. So the conversion is you have liters of solution is maybe in the denominator, and how many moles in the numerator. Or you might need it flipped over. You might need the liters in the numerator and the moles in the denominator. So you would use it just like you would use density or any other conversion factor, just like you would use Avogadro's number. You're going to put the numbers, place them in the right order to get everything to cancel out. Okay, so let me finish reading this. For example, the concentration of a 4.5 molar HCl solution means there are 4.5 moles of HCl in every 1 liter of solution, right? So that's your conversion factor. In this case, 4.5 moles of HCl in every 1 liter of HCl solution. Okay. So whenever I have two things that are equivalent to each other, I can write them this way: 4.5 moles for each liter of solution, or 1 liter of solution has 4.50 moles of HCl in it. Okay? Now these two things are not equal. These are just two different ways to use it, right? When do I use this one? When I want liters to cancel out. When do I use this one? When I want moles to cancel out. Okay, let's look at this example. How many milliliters of 4.5 molar HCl solution will provide 42.1 grams of HCl? Okay. So, start with the only thing that they gave you. You have 41.2 grams of HCl. Okay, so this is a review. How do I get from grams to moles, right? We can only do stoichiometry in moles, even though this one isn't really a chemical equation yet. Well, I need to get to moles. I have to look up the molar mass of this. Hydrogen is 1. Chlorine is 35.5, so 1 plus 35.5 gives me 36.5. That's going in the denominator because I want to get to moles of HCl. Nothing new. That's a repeat, what we've been doing for several months. Good. Okay, now, next question. I want to find out how many liters of solution I need so that the solution contains this amount of grams. So I can use one of these two factors up here. And which one am I going to use? Well, I have moles of HCl here. I'm going to use this second one because I want moles of HCl to cancel. For every 4.5 moles of HCl, that's how much HCl I want to deliver. I need 1 liter of this solution. I don't have to write of solution every time. So this is going to give me the number of liters of solution I need. Okay, and then the last step is it's probably going to give me a small number. I'll convert it to milliliters because that's more handy. But for right now, let's just get the answer in liters. Okay, so I have 41.2 divided by 36.6. And then take that answer and also divide it by 4.50. Okay, I get 0.25. I get a quarter of a liter. Okay, quarter of a liter, not of water, of this HCl solution. Well, how much is that in milliliters? Well, it's 250 milliliters because it takes 1,000 milliliters to make a liter. So 0.250 liters of solution times 1,000 milliliters in every 1 liter Liters are going to cancel out. 0.25 times 1,000 gives me 250. So if I go to the shelf and get 250 milliliters of a 0.45 molar solution of HCl, and I pour that into my reaction vessel, it's the same thing as going to the cabinet and getting 41.2 grams. Isn't that cool? I'm delivering it already in solution. So I guess I could picture of, I could take, here's my solution, there's the HCl dissolved in it, right? If I pour this in to my reaction vessel where we're going to have everything react, it's exactly the same. This 250 milliliters of 4.5 molar HCl will deliver how many little dots? How much HCl? It will deliver the same thing as putting 41.2 grams of HCl in directly if you could weigh it out. And HCl turns out to be very hard to weigh out, right? It's a very strong acid. We never see it in a 100% form. It's always dissolved in water. So whenever you need HCl, you're going to be delivering it this way, already in solution. So the molarity of the solution times the liters of the solution was the way we figured out how many moles of solution we had and ultimately how many grams. So this would be the same as just taking 41.2 grams and putting it in. This is just coming in solution already. Very powerful. Moles is molarity times liters. New way to get to moles. And how did I use that here? I had to divide by the molarity because in this case, right at this step, I had the moles. So moles divided by molarity will give you liters. Let me show you that. We said molarity is moles per liter. Okay? A very handy way to keep this is moles is molarity times liters. Well, what's the third way? Okay, well the third way would be if I wanted to know how many liters and I had the moles and the molarity. Well, that would put the molarity underneath, and that's what I just did. If I'm interested in how many liters I need, I take the number of moles and I divide it by the molarity. So using formulas, if you like formulas better, these are the three ways that you would use it. Probably these two the most. But this third one is what I just did over here. Look, I divided by the 4.5. I used this guy flipped over, which means divide. Okay? All right, one more concept. Let's do a stoichiometry problem with solutions. So when I'm figuring stuff out, I'm not going to run to the balance as much as I'm going to go grab known concentrations of solution and use a pipette or a volumetric flask or something accurate to deliver the right volume of the liquid that I need. Okay, so that's this very last section here. Calculating the quantity of a reactant or product for a chemical reaction in solution. When chemical reactions involve aqueous solutions of reactants or products, we use the balanced chemical equation, the molarity, and the volumes to determine the moles or grams of the reactants and products. Okay, let's do an example. Cover the answers. How many grams of zinc metal will react with 0.315 liters of 1.2 molar HCl solution? So let me write the balanced equation and let's write down what we have. Okay, so we're going to dissect it just like we did in chapter 9, the stoichiometry chapter. I think we might have even done this one. Okay. Only we're going to take one more new tool, and that is Moles is molarity of a solution times its liters. Okay, so this is the overall balanced equation. Okay, I know this is a little too small for you to see, so I'll read the problem to you. Okay, so they ask, the question is, how many grams of zinc? So how many grams of this? So that's going in. When somebody says how many grams of a reactant, you put it on the top because it's going in. And I don't know it, so I'm going to put question mark. I want to find that out. The number of grams of that are going to react with, this time, I don't have a grams here or a moles. I have a concentration and a volume. 0.135 liters of 0.120 molar. Okay, so this is the limiting reagent, right? This is what's the driver. This is how much I have. How much zinc will react depends on this. Yes, I can calculate how much hydrogen I make or how much zinc chloride, but that's not what they ask. They're asking us to relate this to this. And we know we always do stoichiometry, has got to be done in moles, right? It's got to be done in moles. So first I'm going to do it using the formula, okay? And then second, I'm going to do it as a conversion factor. So using the formula, I say to myself, the moles of HCl are equal to the molarity times the liters. So just take those two numbers and put them in. They're both okay, right? They told you had 315 milliliters, which is 0.315 liters. They gave you its concentration at 0.12 molar. Super important. So if I know moles, then I can go and say for every two of these, one of these will react. Remember, we always have to do stoichiometry in moles. We can't do it in molarity by itself, just like we can't do it in grams. If you're given grams, you need to use the periodic table to get to moles. If you're given concentration, you need the volume to get to moles. You need both of these. Moles can only be if you know how concentrated it is times how many liters. So the moles of HCl are going to be 0.315 times 0.12. 0.0378 moles HCl. Okay, well now the rest of the way I'm going to go back to what we learned in chapter 9. When I have moles, I can work directly in moles. So this is moles of HCl. Okay, I don't need to go to the periodic table to get the molar mass because I'm already in moles. So go right to the balanced chemical equation. For every 2 moles of HCl that reacts, put that in the denominator because you want to get rid of it, 1 mole of zinc reacts with it. It's a 2-to-1 stoichiometry. 2 of these for every 1 of those. 2-to-1. Okay, now they wanted grams. If you wanted moles, you would just take this number divided by 2, but they wanted grams. So we need to look up the molar mass of zinc and multiply by it. 1 mole of zinc weighs 65.4 grams. Divide by 2 first, and multiply by 65.4. Okay, 1.23 grams of zinc would react in this situation. Okay, so let's go back. If I had my beaker and I had a whole bunch of zinc down at the bottom, okay, let's say I have like 10 grams of zinc. Okay, and I pour my solution here. I pour 315 milliliters of this solution, HCl on top. So pour that in. This is my 315 milliliters of 0.120 molar HCl. Pour it in. How much of this 10 would react? Well, first of all, hydrogen would be bubbling off of it like crazy, right? That would be kind of cool. So bubbles would be coming off of it. But in the end, I would use up all of the HCl because it's the driver, it's the limiting reagent. And I would use up 1.23 grams of this zinc would be gone from my pile at the bottom. And how much zinc would be left? The difference, right? So that would be 8.77, I believe, right? 8.77 grams of zinc left over. Okay. Or I could have started with exactly 1.23. Let me just make sure that's right. Okay. Or I could have started with exactly 1.23 grams and both of them would be annihilated and basically I'd be left with just salt water. I'd be left with zinc chloride because what's the hydrogen gas would be bubbling off of this like crazy. Okay. All right. Know this is a little bit longer than we had hoped, but let me go back and do this the other way, which is not by using a formula, but by taking my balanced chemical equation, let me just keep that, and using it as a conversion factor. So rather than rewrite this, let me just cover up the top. So it's the concentration part that's the conversion factor. So look what I'm going to start with. Okay, I'm going to start with the only quantity that I know. This is a concentration. A concentration isn't the quantity. The volume is the quantity. Okay, so 315 milliliters is 0.315 liters of this HCl solution. Okay. Oops, sorry, this is not milliliters, this is liters. Okay, that's the liters of the solution. All right. Use concentration as a conversion factor to get from liters to moles. Okay, well, I got liters on the top here. I'm going to need liters on the bottom. For every 1 liter of solution, there are 0.120 moles. That's what 0.12 molar means. 0.12 moles in every 1 liter of solution. Okay, goodbye liters. Hello moles of HCl solution. Okay, if I have moles, I am allowed to go right to the balanced equation. For every 2 moles of HCl that react, 1 mole of zinc also reacts with it. 2-to-1 relationship. Last step, use our same molar mass to get the grams of zinc. Every 1 mole of zinc weighs, got it down here, sorry, 65.4 grams of zinc. So I have exactly the same thing. Instead of doing it in 2 steps, where here I multiplied and then I use that, I use it in 1 step. Use molarity as a conversion factor. Okay, let's get the answer first. It's going to be exactly the same, so I won't redo it. I get 1.23 grams of zinc. So just a second choice. And let me reiterate this right here. Use molarity as a conversion factor. Okay, that's it, guys. We're gonna have one more video in this chapter, and we'll be done.